everyone, and welcome to my session. My name is Tatyana. I'm a software engineer. I work at a company called WillowTree. I mostly do Android development, being focusing on that for almost 5 years now, but I have also done iOS and Xamarin development. And today, I'm going to talk to you about machine learning, and there's a lot of mystery around it, and there's also some truth to this XKCD comic. Sometimes people don't really understand how machine learning works. And so my goal today is to give you a good idea to get started with machine learning in your Android apps, and how much effort does it take to implement a feature and what it would look like in code. But first of all, what machine learning is exactly. So basically, it's the area of computational science that focuses on analyzing and interpreting patterns in structures and data. So basically, it's about learning things from data, and the goal is to get better at predicting results over time. And you may have heard two different terms here. One is machine learning algorithm, and the other one is machine learning model. And so what is the difference between those two? So machine learning algorithm is basically an approximation to some function. It's like a general description of what pattern the data set has. And a machine learning model is going to be the result of training this algorithm and calculating specific parameters. And so you know the exact parameters and the correlation between inputs and outputs. And of course, there's plenty of different machine learning algorithms out there. And so we possibly can't just focus on all of them here in the talk. But I did want to call out that there's a cool playground for neural networks that was created by TensorFlow. So it allows you to create your own neural networks right there on your browser and just supply different kinds of data and see what comes out with different neural network architectures. So I really recommend to check it out if you have time. And before we even go into the woods with machine learning, a good question to ask is, can my task be solved with machine learning? And the first thing to remember is that it's all going to be dependent on data. So if your data does not have if your data has some flaws, or you don't have enough data, you can't rely on machine learning to provide access to any knowledge outside of that. And of course, it's really important to get to know the domain and do user research. So one example could be, like, say, for example, you have a client and it's a grocery store, and they want to use machine learning to predict some sales. And you ask them, okay, so do you have any data? And they say, yes, we do. And then you look at their data, and it turns out that they have only collected it for 3 months, and it was during Thanksgiving and Christmas time. And so obviously, if we're trying to predict future results based on just that data, it's not going to be accurate. And so there's always some domain knowledge necessary. And as always in software engineering, we have to think about edge cases and make sure that your data set is inclusive. So for example, if you want to do things like facial recognition, and if you're working with images of people, it's really important to make sure that in your data sets, you're going to include different facial features and different colors of skin. Then one issue that can happen with machine learning is overfitting. So that means that your model performs well on training data, but it doesn't do good at all on the new unseen data. And so it's really important to remember that if it is working with a simple example, it doesn't mean at all that it's going to work just as well with a more complicated or sophisticated one. And let's look into some more bad use cases for machine learning. And so we talked a little bit about extrapolation already. But when you have to take into account different factors when you're trying to predict results from the past, like, for example, if you want to predict sales, and a new big company, your competitor, is entering the market, but your data doesn't account for that. And also, it can be the case where you have user segments that can vary significantly. So, for example, you have an app that allows people to book doctor's appointments, right? And you want to suggest them what would be the best time to schedule your next visit, but you have to remember that there's going to be different kinds of people going to that doctor. So it's going to be people that are mostly healthy, and they just come in for a check-in. And there are people with, for example, chronic illness that will need to visit this doctor more often. Another good question to ask is, can a human do this successfully? So say, for example, you want to create an app that detects allergens from images of food, like, for example, say you're allergic to gluten. And I'm not sure that this app could actually be successful because on the top row here, we have images of bread with gluten. And on the bottom row, we have images of gluten-free bread. And so if you just point the camera at this bread, can you really tell the difference between them? Because I know I can't just by looking at them, but maybe you can, but then you must be really special. And another question that comes up often is, how much math do I need to know in order to do machine learning in my app? And the short answer is, you don't really need to know math in depth to use machine learning frameworks, but it certainly can help you if you run into some kind of issues and you want to troubleshoot them without the help of a data scientist. So let's take a look at the overall machine learning process. So what does it involve? Well, first of all, you would need to gather your data. You have to prepare it and clean it. You would have to then select a machine learning model, or you can choose the existing one built by somebody else. Then you have to train this model on the data set. And one thing to remember here is, don't use all of your data set for the training. You need to set aside a part of your data for later testing and evaluation. And then the next step would be evaluation of the model against the data that was initially excluded from the training set. Then you might have to tune the model some more, meaning that you might have to adjust some parameters that are not dependent on data. And finally, last step is actual prediction or inference. And inference can be happening in the cloud. So that means that your machine learning model would not be directly accessible, and you as a client would be making network calls and passing your data to the server. And other option is to have the model on device. So that means it will be stored locally, and all the operations will be performed strictly on your device, and there will be no network calls involved. And also you can set up something custom, so you can technically could spin up your own server and upload your custom model, and just you could even switch between custom model and server and local custom model. What are the pros and cons of cloud machine learning? Well, probably the most obvious one is simplicity. So you don't really need to know hardly anything in detail about the internal architecture of the model. You just need to be able to make network requests and responses, which is a really common task for us as developers. And you don't need to worry about training, retraining, optimizing the models, fixing bugs in the model. And you don't need to worry about some platform-specific issues either. The biggest cons are pricing, because usually these cloud services will be charging you for a certain amount of network requests, and it can get expensive pretty fast. Another con is a lot of times it'll be limited in how you can configure this model, and if you have some interesting specific use case or a common data type, you probably wouldn't be able to find a cloud ML service that will fit your needs. And obviously it cannot work without internet connection, and it won't be good either for any kind of real-time processing, because it takes time for the network request to be sent, and then you have to be waiting on the response, and your user will most surely notice that. And finally, there are some privacy concerns and risks that can come with passing some sensitive data, like, for example, your financial or health information. And so in this presentation, we'll be focusing mostly on device machine learning, and it's a big trend on mobile in the past couple years. And specifically for Android, in Android P, machine learning was integrated into the entire operating system. It's being used to predict when user is going to use a certain app at a particular time. And in Android Q, Smart Reply was built into the notification system, and it became available in all messaging apps. And in Android 10, Smart Reply can now suggest an action. So, for example, it could be opening a map. And here are some other cool examples of on-device machine learning features. So we have live caption, and Google Lens suggestions, and Google call screening. And if you have been watching the hardware news as well, so you may have heard the term AI chip. So what that is, it's basically a neural processing unit. So it's a microprocessor that specializes in acceleration of machine learning algorithms. And so those NPUs have been included into latest devices that have been coming out. And one good example is Google's Pixel Visual Core. So it's an image vision and AI processor that was first featured in Google Pixel 2. And there's also one interesting website that allows you to compare device performance on different machine learning tasks, like, for example, image classification, object recognition. And you can go there and see how different devices rank and what their benchmarks are. Looking closer at on-device machine learning, so there are some obvious advantages. So if you're working with some kind of real-time processing, like, for example, you're manipulating a live video, or you're doing something with augmented reality, like, for example, this InstaSaber app is a pretty fun example. You would want to use on-device machine learning there. And if there's issues with connectivity, which unfortunately, there are still a lot of places in the world where access to internet is not available at all, or it's bad, and we want to account for that user segment as well. Some other advantages is keeping things private, so meaning that the data will never leave the user's device, and a lot of people wouldn't be comfortable with certain kinds of personal data being sent to the servers all the time. It also means lower costs. So if you run models on device, that means you won't need to pay for hosting your models and paying for those requests to cloud services. But there are some drawbacks, of course, as well. Even though the mobile hardware has been advancing really fast and it's becoming more and more powerful, we're still in a limited resource environment. So we need to remember that inference or prediction is a heavy computational process, and so that means it may increase the battery power usage, so we should notice the battery health. And also, there's trade-off between performance and accuracy of the model. So models of smaller size tend to be performing faster, and they also tend to be more energy efficient, but they can be less accurate. And so, again, a lot of things can depend on your use case. So say, for example, you have an app that you want to use for detecting some kinds of poisonous plants. And of course, you cannot risk your accuracy there because the consequences will be much worse, as opposed to, like, for example, you're just labeling cats and dogs. Other drawbacks is that certain models can take multiple megabytes of memory if they're bundled with the app. In order to mitigate that, we can just download the model after app installation or just try to use smaller model. Then we should also think about how we're going to update our machine learning model. So say, for example, we have a flaw and we need to push it out urgently to the users. So does that mean that we should force all the users to upgrade the app as a whole, or should we just try to update your machine learning models in the background and deliver them to users maybe without them even knowing? And also, we all know that apps can be reverse engineered, and that also means that your machine learning model can be stolen. So now let's move on to frameworks that we can use for machine learning in Android apps. And we're going to be looking at TensorFlow Lite and MLKit today. And of course, there are some third-party SDKs as well that could be worth checking out, but we're not going to cover them today. OK, so TensorFlow Lite is basically a lightweight version of TensorFlow framework specifically for Android, iOS, and embedded devices like Raspberry Pis. Its biggest feature is that it enables on-device machine learning inference. It supports hardware acceleration through Android Neural Networks API, and its operators were tuned specifically for performing on mobile platforms. And one cool thing to know is that there are some TensorFlow Lite models that are ready to use, so they were built already for you by TensorFlow. And I'm going to do a quick overview of those. But I also wanted to say a few words about the Android Neural Networks API. Although we as app developers don't really need to know about it in detail so much, I think it deserves a mention. So what it does is distributes the computational workload between specific neural network hardware units on your device. So that'll be GPUs and digital signal processors. And machine learning frameworks like TensorFlow Lite will be using it to perform hardware-accelerated inference operations. And it's available on devices running Android starting from 8.1. Another cool feature in TensorFlow Lite is GPU delegates. So basically that means that it takes advantage of the GPU of your phone. When it does that, the speed up can be really significant. You have a couple of charts here for detecting face contours and video segmentation on different devices. We can see results are pretty noticeable. However, on small models, the speed up might be really small, so it might not be worth it. Also, the GPU operations that are not supported will be automatically falling back to CPU. Okay, so what is the outline of implementation steps for adding TensorFlow Lite model into your app? So, well, first of all, of course, you have to choose a pre-trained model or create your own custom model. If necessary, you have to convert it to TensorFlow Lite format and optimize it. And then you would have to actually add the model into your app. So that means you would be loading the .tf Lite model into memory. And then you would have to grab the input data from users. So, for example, that could be image from your camera app. And you'll probably have to transform it into the input data format that's expected by the machine learning model. Because the machine learning model's inputs is not expecting a full image from the camera, so you might need to resize the image, and usually it's going to be an array of floats. And then you'd have to build a class called an interpreter. So basically that's a class that runs the prediction or inference. And then you would retrieve the inference results and interpret them in a meaningful way. So you don't want to just show users an array of floats. They wouldn't probably appreciate it. Okay, so what are some ready-to-use TensorFlow Lite models? So you can check those out on the TensorFlow website. So that's image classification, object detection, pose estimation, smart reply, segmentation, style transfer, text classification, and question and answer. And today we're going to look at an example for pose estimation. I thought it was a fun one. Maybe it's because I like dancing. Pose estimation model is called PoseNet, and it estimates where person's key body joints are. So it could be like, for example, your left wrist or your right knee. And it has a concept of key points. So key point would be like a specific body joint, like for example, your left wrist. It will be coupled with a coordinate, an XY coordinate of where it's located. And then the confidence score. So basically that means how sure the model is that this specific body joint is located in that particular coordinate. And there is also this parameter called output stride. So basically that shows how much the output image is going to be scaled in relation to input, and that would affect the number of key points being processed. And so we can see that with higher output stride, we'll have faster performance but lower accuracy, and with lower output stride, we'll have slower performance but higher accuracy. So we have some options there. Okay, so let's take a look at some code examples here. Well, obviously, we'd have to add a Gradle dependency for TensorFlow Lite Android support library. There's also an option that allows you to select specific ABI architectures. One thing you have to also do is you need to ensure that Gradle won't compress your TensorFlow Lite models when you're building the app. So you have to add this no compress option here. And then, so these code examples are based from official TensorFlow PoseNet example. So for the reference, you can look into the PoseNet class. So here we can see that it's creating the TensorFlow Lite interpreter, and it's setting some options. You can see it's adding a GPU delegate that we talked about earlier, and it also shows you how to enable the neural networks API to use hardware acceleration. And to initialize the interpreter, we have to pass it the model file, and machine learning models usually would live in the assets directory of your project. So this is how it's going to look. So the load model file, loading the model into memory from assets. And then since it's post-tracking, we'll need to grab images from camera. We'll have to set up the camera preview. And all of this code is available in the example, but I'm not going to focus on it in this presentation, since it's mostly about machine learning. But basically, once we have an image available from the camera, they will have to create a byte buffer from that. And then, as I mentioned earlier, we need to perform some image manipulations. So in this specific example, we'd have to convert it to RGB format, have to rotate and create a bitmap, crop and scale it, and then run the post estimation method on the postnet class. And then in that estimate post method, we have to tell the interpreter like what the inputs and the outputs are. And so image is going to be represented in the byte buffer of float values, and they're also going to be normalized. Then we're going to pass the inputs and outputs to the model. And then in the output array, we'll be looking for, so it's going to be kind of like a heat map. So we're going to find the rows and columns and where the key points of a person are most likely to be. And again, I'm going to point out that key point is a body part from a predefined enum. So it could be like a list of things like your wrists, your knees, your nose, and everything else. And it's also going to have its coordinate and confidence score. And then finally, you would have to draw results on the camera preview. OK, so now let's talk about how do we convert models to TensorFlow Lite format, because a lot of times we'll be using, in order to build our custom models, we'll be using the TensorFlow framework or a Keras framework, but we cannot just include models produced by those frameworks into our mobile app. We'll have to convert them first into the TensorFlow Lite format. And so the input can be a TensorFlow model, a protobuf, or a Keras model, HDF5. And then here's an example of how you would perform that conversion. So it can be done in command line, or it can be, it's recommended to use the Python API for that. Overall, I would say it's fairly simple. So we'll be just calling the convert method on the TensorFlow Lite converter. And now let's talk about how we can optimize the models for mobile devices. And one of the really common techniques that's being used is quantization. So that basically means that we're going to be changing the precision of our machine learning model. And I think a really good example is weather forecast, right? So say, for example, you're looking at the forecast and you see that it's going to rain. And how much information do you actually need? Do you want to know the exact amount of droplets per second, or it's enough to just say, OK, it's going to be light rain or it's going to be heavy rain? And so that means that sometimes we don't really need super high accuracy. And so we can optimize the model to perform better. And so during quantization, width will be transformed from floating point to 8 bits of precision. Here are some charts on how they can affect model sizes and accuracy. So I have to note that this example is for specific image classification models, MobileNet and Inception. So that can vary for different kinds of machine learning models. But here we can clearly see that the larger the model is, it's going to have a higher accuracy. And then we can also look at accuracy versus latency, so like how accurate or how fast it performs. And here in this chart, we can see the MobileNet image classification models, the 8-bit quantized version and float version. And we can see those results are pretty close. But the trend is that higher latencies also usually means higher accuracy for models. And again, it's always going to depend on the model and your specific use case. What's more important to you, higher accuracy or higher latency? So there's like no one size fits all. So you have to like think about your domain and think about your use case and think about your user base, like who's going to use your app. And TensorFlow has some benchmarking tools linked here, and you can also use a tool called TensorBoard that will allow you to visualize the model graph and operation it performs, and plot some metrics to see how different parameters affect performance. So how do we enable this quantization in TensorFlow Lite Converter? So it's fairly simple. So you would just have to add the optimize for size flag in that Python snippet. And of course, I mean, it's not everything I told you is not exhaustive. So there's more things you could do with post-training quantization. And to just kind of sum it up, post-training quantization is going to reduce the size of your machine learning model, is going to lower the prediction time, and usually the model accuracy is not going to be affected too much. And it can also possibly be recovered after retraining the model. And so I'd like to refer you to TensorFlow optimization guides for that, so you can discover on your own what works best for your use case. Okay, now let's move on to Firebase MLKit. And you probably know that it provides a lot of out-of-the-box solutions for Android and iOS. It allows you to do on-device or cloud machine learning, but it can vary by the API. And also have to note that for cloud APIs, there's going to be pricing plans applying for that. Other cool thing about Firebase MLKit is that it can host and serve custom TensorFlow Lite models to your app, and you can configure when you want to use cloud-based model or on-device model. So just a quick overview of all the features that MLKit offers. So we have text recognition, we have face and object detection, barcode scanning, image labeling, landmark recognition, natural language processing and smart reply, AutoML, Vision Edge, and your custom models. And of course, I wouldn't be able to cover everything today because it's just like really too many things. So I decided to focus on smart reply, AutoML, Vision Edge, and also going to show you some examples of how to use it with a custom model. Okay, so what would be like the basic workflow for MLKit Base APIs? So first of all, you would have to set up Firebase for your project, and in your Firebase console, you would need to enable the cloud-based APIs if you want to. Then you'd have to add the MLKit SDK into your app. Again, we have to prepare the input data, so it could be capturing image from a camera or preparing a text that you want to be analyzed. Then you'll be passing your data to the machine learning model, and then you'll perform inference and interpret the results and present them to user. Okay, so smart reply, I'm sure you're all seen this, so it's just these little suggestions that pop up when you type a message. And a smart reply model checks up to 10 of most recent messages from conversation history. Also, it's important to note that it detects the language of the conversation, and as of this time, it's providing suggestions for English only. And also, other thing is that it's not going to provide any suggestions at all if it discovers that it's a sensitive topic. And it can give you up to 3 suggested responses. Okay, so how do you configure your project to use with smart reply? So we have to add some Gradle dependencies here. Then you would need to create the conversation history, and that would be the chronologically ordered list of Firebase text message objects. They also have to be sorted, so the earliest timestamp should go first. And when you create these Firebase text message objects, you also need to pay attention of what user you created for. So you can see there that we have create for local user and create for remote user methods. And so local user is the person who's using your app, and the remote user is the person that the user of your app is communicating with. And so you need to pay attention there, like not to confuse these two, because they'll affect the result of suggestions. Okay, so then how do you get suggestions? you have to get an instance of Firebase natural language and call the suggest replies method and pass this conversation list that we created earlier. And it's going to have listeners for success and failure, and it can give you an error that the language is not supported. So that can happen. So yes, and then you just retrieve the results and show them in your app. So really pretty simple overall. Okay, now let's move on to AutoML Vision Edge. So you may have noticed that MLKit has the basic image labeling API, and it also has the AutoML Vision Edge. So what is the difference between these two? MLKit Base Image Labeling API can recognize around 400 types of objects. But the thing is, it's only limited to around these 400, and those are like, just completely random objects. So most likely for your app, you would want to recognize some specific type of object, like for example, like say type of flower, right? And so chances are MLKit's base image labeling API is not going to have labels for those things. And so AutoML Vision Edge is going to work better for more narrow domains. And so that means that you would have to provide your own images and train the AutoML Vision model. And also, important thing to point out, if you're going to work with images of people, Google has created this inclusive machine learning guide, so you should definitely check it out and make sure that your data set of people is inclusive, includes different kinds of skin, different kinds of facial features. So how can you supply your custom training data to AutoML Vision Edge? So that could be in a structured zip archive with the images. It could be uploaded to cloud storage. It can have CSV index. Or it can just be unlabeled images, and then you would label them manually in Firebase console. So what is the process of working with AutoML Vision Edge? So first of all, we'd be training your model using your images. And then you would have to select model latency and size. So again, this would be dependent on like your use case and what you want. And then you'll be able to evaluate the performance metrics for the model and make some adjustments and tweak parameters if needed. And then you can publish the model and make it available for your app. And then the example link below shows how to use this API in the Android app, and how to add it to your project. Okay, so now let's move on to using custom models with MLKit. And just a quick overview of features it has. So you can host your models using Firebase. That's a great thing, so you can make sure that your app is always using the most recent version of machine learning model. You can perform the inference in the app, and the model can be also bundled with the app, or it can be hosted in the cloud, so you can have like different options there. You can specify multiple model sources, so you can use the local model when the network is unavailable, or otherwise switch to cloud model. And you can configure the conditions under which your app will automatically download the new versions of the model, so you can make sure that it's only happening when device is idle and charging on Wi-Fi, all these things. So the workflow for this, you have to build and train your TensorFlow model. You have to convert it to TensorFlow Lite format like we discussed earlier, optimize it, then you can host it with Firebase, and then use it for inference in the app in a similar way like we talked about before. Okay, so setting up the project for this case, we have to include the Firebase ML model interpreter dependency here. And if you're going to use Firebase hosting and cloud services, you would also need to add the internet permission. And of course, we need to, again, make sure that Grail will not compress the models when we're building the app. Then we'll have to specify remote model names, and so that's going to be done with Firebase custom remote model builder class. And here we can also specify model download conditions. So we can require it to use Wi-Fi. And Firebase Model Manager class allows to download the remote model that you specified with the conditions you provided. As far as local model goes, you can just use the Firebase custom local model builder and just direct it to the asset file path in your project. And then you can create the interpreter for a local model, in a similar way for a remote model. First, you would want to check if the model was downloaded. So you can use Firebase Model Manager isModelDownloaded method. And then add an unsuccess listener. So if the model was downloaded, then you can use the Firebase Model Interpreter options and build the interpreter for that. Or otherwise, you can fall back onto the local model. Yes, and so Firebase Model Manager download can will also perform it under the conditions you specified earlier. And it can have the incomplete listener that let you know that download has been complete. Okay, so what if we borrowed somebody else's custom model? Well, we're not exactly sure what it takes as input and output. So there's a tool called TensorFlow Lite Python Interpreter. It allows you to inspect your model, and so it can get you the input details and types of what the machine learning model is expecting. And so finally, the inference. So we'd have to, because it's a custom model, we have to set up the input and output format and the data types here. And then finally, run the inference. And we also have the success and failure listener here. And then finally, you would have the outputs. That will be probabilities or confidence scores. And then you have to present them to the user in a way that makes sense for them. Okay, so to sum everything up, today we looked at TensorFlow Lite and MLKit as well. So TensorFlow Lite will be best for device-only machine learning, and it's also completely free. Then Firebase MLKit can handle some advanced configurations. So like if you want some kind of system or solution to handle your model updates, or like be able to switch from cloud to local machine learning, then this will be your best option. Also have to emphasize that data is really important. So if you're collecting your own data sets, please make sure that you're thorough and inclusive with your data. Think about edge cases. Also, it's important to give yourself some time for optimization and experiment with models, because sometimes you may not receive the results you wanted. And you have to be, while optimizing models, you have to be also mindful of accuracy trade-offs. And think about when you can sacrifice accuracy and when you can't. And this accuracy trade-off is going to be model-dependent and use case-dependent. So basically just make sure to give yourself enough time to experiment, because pretty sure you notice that like the code itself, the implementation isn't that hard. So you just like look at the documentation, include Gradle dependency, and then just like follow the instructions, and it's pretty much straightforward, right? So the tricky part here is the optimization and data. So if you're going to add machine learning to your project, please give yourself some time to experiment with that and tune it and optimize it. And as a final word, I would like to encourage everyone to just play around with machine learning and have fun and experiment. I think you'll enjoy it. And also I hope you enjoy the rest of your time here at droidCon. Thank you very much for coming. And if you have any questions or feedback from me, I'll be happy to talk to you.